Hello students, welcome to the next lecture, lecture number 15. So in this lecture we will be discussing about turn off characteristics of an SCR. So by the end of this session you will be able to describe the turn off characteristics of an SCR and turn off methods of an SCR. Okay. So when we say turn off, you know that the thyristor can be operated in two modes. Either it can be in off state, that is as an open circuit, or it can be in on state as a short circuit, right? So in most of the applications, as we know, the thyristor can be used as a switch. Okay, it can be conducting, that is, it can allow a large amount of current to flow through it, or it can be in an off state. Okay, and in the previous session we have already discussed how to turn it on. Okay, just by giving a gate signal, a small gate signal is enough to turn on the device, right? So according to the example what we discussed in the previous session, a small amount of current as small as 10 milliamps is sufficient at the gate terminal to turn on the device, right? So whereas turn off is not as easy as we think. Just by removing the gate signal, the device will not be turned off. The SCR will not get turned off even if you remove the gate signal. Okay. So what exactly do we have to do when we have to turn off, right? So we actually have to bring down the anode current. Okay. So anode current is nothing but the current flowing through SCR, right? So we have to bring this anode current below holding current. Okay. What is holding current? Holding current is the minimum current that keeps the SCR on, all right? But below that, below holding current, the device will turn off. Okay, you know the definition. So, and we are also should be aware that this anode current usually will be 1,000 times greater than the anode current value. All right. So, to turn off the device, the anode current has to be brought below holding current. All right. So imagine we have done. All right. Now say imagine the device is in a state of getting turned off. All right. Now say if you apply a forward voltage, then immediately the device will turn on because it is not in a state to block the forward voltage. All right. So why is that? What is the reason? Because there will be still charges that will be there in the 4 layer or the 3 junctions, okay, which when you apply forward voltage, okay, even after bringing the anode current to 0 level, if you apply forward voltage, then immediately the device will turn on. Okay, so this situation has to be avoided. So turning off is nothing but first condition is you have to bring the anode current to 0 level, and you have to bring also the device to an ability where it can block the forward voltage. Okay, so that is nothing but turning off of a device. So exactly the turn off time, now we can define it as the minimum time interval between the instant at which anode current becomes 0 and at the instant at which the device is capable of blocking the forward voltage. All right. So to do that, what we have to do to make the device to block the forward voltage, what we have to do, we have to apply reverse voltage, because as I said, because of the trapped charge carriers that will be there at the 3 junctions, to make these charges recombine or to eliminate all these charges that are trapped, you have to eliminate them, right? So to eliminate them, you have to apply a reverse voltage across anode and cathode. So that's a procedure to turn off the device. So first let us understand what happens when there is turning off of the device. Later we will discuss what are the different methods to turn off the device. All right. So the as you can observe, the turn off time is illustrated by the waveforms as you can see, and total turn off time period it is divided into two sections or two intervals. Okay, first is reverse recovery time, small t suffix small rr, and gate recovery time, a small t suffix gr, gate recovery time. All right, so let us see what exactly happens. So during this turn off condition, when you are turning off the device, what are you exactly doing? You are bringing the anode current to zero, isn't it? So observe that the moment or the at instant t1 when anode forward current becomes zero, okay, between T1 and T3 is where the reverse recovery time, we call it as reverse recovery time. So what is happening there? If you observe from T1, after it crosses zero, the anode current reverse its direction. That means it starts flowing in the negative direction. Okay, it starts flowing in the negative direction. Say at instant T2, you have applied the reverse anode voltage. Instant T2, you have applied the reverse anode voltage. Okay, then the reverse recovery current continues to flow in the reverse direction. Okay, or continues to decrease when you are applying the reverse voltage. Okay, it continues to decrease, but after sometimes after applying reverse voltage, you can see now slowly the anode current is now raising up. Why is that? Because when you apply reverse voltage, now junction J1 and J3, they are able to block this the reverse voltage, and the recombination of the charge carriers at junction J1 and J3 has taken place. Okay, now that will cause the anode current to start develop. Okay, it starts raising up now, but still the device is not in a state to block the forward voltage. Okay, so what happens? Even say you have continued the reverse voltage. So during this time, when there is reverse voltage applied, during this time period between T3 and T4, this is the time taken by the trapped charge carriers that is there, that has got trapped in junction J2 to recombine. Okay, so this we call it as gate recovery time, GTGR, gauge recovery time. So this is the time taken by the trap charge carriers to recombine from the J2 junction. So after T4, if you observe that, then the recombination would have been completed. Okay, and now the device will be able to block the forward voltage. Now if you apply forward voltage, even now if you apply, then it is in a condition to block this. That means what? Now at this time the device is turned off. Okay, so totally the time of total time of, you can take it as TQ, because this is the total duration for the recombination to take place. Okay, actually T off is summation of a reverse recovery time and the gate recovery time. But if you observe, even say if you, even after you apply the positive forward voltage, the device should be in a condition to in an ability to block the forward voltage. Okay, only then we say that it is turned off. Correct? Okay, now as we know, turning off of the device, to turn off the device, what do we have to do? We have to bring the anode current below the holding current. Okay, and by applying reverse voltage to the device, by applying reverse voltage to the device for the time duration larger than T off, for the time duration larger than T off, you have to apply the reverse voltage. Okay, only then you can turn off the device. I hope you are getting it. All right, now this total reverse recovery charge for the duration TQ, how much time is it taking for the total recovery? Okay, it actually depends on the magnitude of the forward current, right? Obviously, right? When like how much is the magnitude of the forward current, accordingly that much more of charge carriers that would be there available in the device, right? Okay, so at what amount, how much of anode current is there, based on that this reverse recovery time also depends. Okay, and also of course the second point is at what rate is it decreasing. Okay, at what rate it is the reverse recovery charge of the thyristor depends on the magnitude of the anode current of the uh, forward current just below the turn off condition and at rate at which it is decreasing. Okay, so that will actually give us the total time for turning off of the device. All right, so if you observe, so this turn off time, it can vary depending on the circuits. All right. So as we had discussed in the previous session as well, in the inductive type of loads, the time duration will be varying, and if the load is a RC type, then the time taken will be again different. All right. So if the thyristor is taking time, turn off time around 50 to 100 microseconds, then we say that it is a slow switching device or slow switching thyristor. If the thyristor is taking turn off time between 10 to 50 microseconds, then it is fast switching thyristor. That means we want the switching to take place faster or slower, right? So based on that, we'll say we can categorize it as the device is slow or a fast switching device. Okay. So just to wrap up now, like to turn off the device, what's the procedure? As I just now mentioned, when the device is already conducting and there is current flowing through, there is sufficient anode current flowing through. Okay, then even if you remove the gate signal, then the device will not turn off. Okay, so to turn off, what do you have to do? You have to bring this anode current to zero or below holding current. Okay, so even after you have brought the anode current below zero, okay, even now if you apply forward voltage, the device will turn on. Okay, so you have to avoid this situation. To avoid that situation and to complete the turn off process, what do you have to do? You have to apply reverse voltage across anode and cathode. So based on that, you have three conditions, three methods to turn off. One is, say you have this circuit where you have connected this V across anode and cathode terminal, you have the load. Okay, say if you have a switch, a simple switch in the circuit, if you just open the switch, okay, opening the switch, you can make the anode current reduce to zero, right? Or the other way is you have to increase the impedance of the load. All right, increase the impedance of the load. Or another method is you use some shunting circuit. Say you connect some parallelly, you connect some commutating components, which we'll be discussing. Okay, which we'll be discussing in further sessions. If you connect commutating components across, that is in parallel with the device, then you can turn off the device. All right, so all these are different methods of turning off. So as I said, the second method is apply reverse voltage across anode and cathode. Apply reverse voltage across anode and cathode. And the third method is apply negative signal at the gate terminal. Okay. One is using natural method, natural commutation, which I'll in a few seconds I will explain what it is. First is natural commutation. Second is applying reverse voltage across anode and cathode. And third is applying reverse potential or reverse signal at the gate terminal. So there are mainly the three methods to turn off the device. So as I mentioned, yeah, commutation means what? It's the process of turning off the device. Okay. So in order to turn off the device, there are different circuits. All right. We call it as commutation circuits. So categorized into two methods. One is natural commutation, also called line commutation, and second method is forced commutation. Okay, one is natural way. Natural way means what? you can directly use a supply signal to turn off the device. How do we do that? In natural commutation method, where in the AC supply, okay, we know that the AC voltages at every half cycle it passes through zero, right? So this reverse voltage, reverse supply voltage will be turning off the device. So naturally you are using the supply signal to turn off the device. That's why it is called natural commutation. And since you are using the supply or the line as it is for turning off the device, it is called line commutation. Okay, and the advantage is that it doesn't need any external circuit to turn off the device. So simple examples are rectifier circuit, AC voltage controllers, cycloconverters, which we'll be discussing. Okay, and what is forced? Forced commutation means what? It's nothing but you are using some external circuit where you are forcefully turning off the device, isn't it? Okay, so that's why the name forced commutation. You are forcefully designing circuit wherein you are diverting the anode current to flow in some other path wherein you are reducing the anode current. So forcefully you are turning off the device. So there are different classifications there, class A, class B, class C and D. For your syllabus you have class A and B, which we'll be discussing in the further sessions. Alright. So this is a simple example for natural commutation. Just for your information, I've put this. Let me explain that. This is SCR or the thyristor, a simple half-wave rectifier circuit. As you can see, the SCR has replaced the diode here. At the input, you have the AC supply. Vs is your AC supply, all right? And this is your SCR. And remember, there is the gate drive circuit is not shown here, but there will be there because you have to use it to trigger or give gate signal, right? So Ig is my gate current that will be applied here at the gate terminal, okay? And we know that whenever gate signal is applied, only then the SCR will turn on, okay? When SCR turns on, then there is a flow of current in this circuit. The circuit is only complete only then, isn't it? Okay. Now imagine you have connected a CRO across the load. Okay, you have connected CRO across this RL, and you are measuring output voltage and output current. So V naught is my output voltage and I naught is my output current. All right. Now, if you observe, this is my supply, which is AC supply, which is varying continuously, right? So till I give gate signal, see here, till the supply voltage at this stage, till I give my gate signal, the SCR will be in off condition, isn't it? Off condition. So whatever you measure here, you will not get any output at the load. Okay, there is no output at all. After you give the gate signal, after you apply a pulse at the gate terminal, the SCR will conduct and there is completion of this circuit, and the voltage what you apply here, that will be flowing to the load as well, right? Of course, in the in a lesser magnitude, as we already know. Okay, so the voltage what is applied, that is visible at the load. Okay, even the current, as you can see. Now, as in the next half cycle, when the supply voltage crosses zero, it goes reverse, right? So the reverse voltage, when it is applied to the anode terminal, now the SCR turns off. So when the SCR turns off, you don't get any output at the load. I hope you are able to understand. Again, when it reverses, when it goes positive, at this duration, you can see still now, till this time, SCR is not turned on. Why? Because you have not applied the gate signal. So once you applied the gate signal, the SCR is turned on, and the same voltage what is applied, what is supplied is visible at the load. Okay, this is your output voltage and output current. I hope you are able to understand. Okay, So this we will go in detail with the derivation, equation, expressions, everything in the coming sessions. All right. Okay. So this was used to explain the natural commutation. Natural commutation is nothing but line commutation where you are using the supply, AC supply itself to turn off the device. All right. So the reverse voltage is turning off the device. Next, as I mentioned, if at all, if you might ask, what if my input is DC? Okay, so DC you cannot use it to turn off. Yeah, you are aware about that because it will be constant in one magnitude. All right, so you cannot use it for um, the natural commutation. So you have to use some other methods to turn off the device. So if you are using some external circuit where you are forcefully trying to turn off the device. So how do we do that? Forcefully means what? When I use the word forcefully, it means I'm trying to divert this current of the SCR into some other path, okay, which again I'll call it as commutation method, okay, divert the current to flow in some other path so that you are reducing the anode current of the SCR, and that will in turn eventually it will turn off the device. Okay, so forcefully you are turning off the device. Oh, that's why the name is forced commutation. So examples are choppers and inverters, okay, which we'll be discussing in the coming sessions. All right. I hope it is clear. Please go through the recording. If you have any doubts, please get back. See you in the next session.